Well, I think one, we've been on a journey of learning what intelligence really means. And we're not there yet. We're a lot closer. We've learned what it's not entirely. You know, it's things like math and logic, which were kind of the basis of early work in AI, is obviously part of what humans do that's intelligent, but there's a lot of things that we do that isn't kind of math and logic based, you know, like emotion and creativity and things like that. A lot of things that were easy for the early technology approaches to do really opened up things that were hard to do later. So like common sense reasoning, you know, being able to do what a 3-year-old can do. You know, a 3-year-old knows that if he lets go of something, it's going to fall and hit the ground. You know, we don't have computers that know that very well. There's a few that are starting to get there. They're starting to give it that kind of capability. But we started out kind of jumping to the end goal. If you look at things like the Turing test, which is, you know, a common test, it was really about trying to trick, you know, not really trick, but trying to have a computer that a person couldn't tell if it was a human or a computer. And what we found is that actually isn't a very good test because it's easy to spoof. You know, if you trick a person, there's lots of people who, you know, play like they're somebody else and fool people. So that didn't turn out to be as good a test as we thought to drive research. A lot of things too, we had a lot of great ideas that the hardware and the software technology weren't ready for. I think one of the things that's reason why this is starting to come back around and people are starting to get much more enthused about making real progress is that we have so much more capability. You know, the systems that we work with now have increased in power so many fold over what we started with. In fact, I think one of the areas that's going to be very fruitful is looking at some of the old, really old thoughts in the very first years of computers when people didn't know what they were going to use with them, and then applying them in these new high-powered computer systems that we have. Before we had operating systems and word processors and, you know, GUI systems and all the kind of things we all take for granted now, computers were a lot more open-ended. You know, people could create something using the electronics and the memory and the processors that was, you know, there weren't really standards. If you were going to create an application, you kind of had to start from scratch and put it all together. And after we started building all these standard systems and platforms that we, you know, became very used to, they gave us a lot of productivity, a lot of good business value. But it also kind of locked us into a certain way of thinking about how to use computers. And I think one of the things that's changing is people's willingness to look beyond kind of current models and look at new kinds of models. When we start talking about computers that are smarter than people, or even developing ones that are, we don't even know how to build systems that are as smart as people. Not even as smart as, you know, mammals of much smaller scale than us. I think that when we start talking about developing intelligent systems that are general purpose, hence the kind of artificial general intelligence moniker that you hear people using now, we're talking about things that would have the kind of learning ability, kind of free learning, autonomous knowledge acquisition capability. So just like you know, you walk into a new situation, you kind of have to figure out what's going on, how does it affect you, you know, what are you going to do in that environment, how much you utilize what's there to help you reach your goals. You know, building a system that's capable of that doesn't mean it's smarter than a human, but it could be a very useful system, and we don't have systems like that yet. Now, when you start talking about a large part of the conversation at this conference is what would happen if we created one that was smarter than humans. The notion of the singularity, that it would take off and leave us behind and maybe to our detriment. I personally think we're so very far away from that in our lifetimes we're not going to have to worry about it. But I do believe that probably in the 10 to 15 year time frame we'll have interesting AGIs. We'll have systems that have very interesting capabilities that today, if we had one today, you'd say it was a revolution. By the time we get there, just like lots of advances we've made in artificial intelligence, by the time we get there, everyone says, oh, that's not real AI, it's something else. So we'll develop very useful, interesting systems, and there's a new wave of that happening now. I think we'll see a lot of interesting advances over the next few years, but one taking off and leaving us behind, I really don't believe in. The interesting point there is that we're actually reaching an interesting kind of diminishing returns with kind of classical Moore's law, and that's where you've noticed now that you know, laptops, the high-end laptops have 2 processor cores per chip. You know, we've gotten to the point now to where just making one chip, one processor, faster and faster and faster is starting to get where we can't keep pushing it because we're running into physical limits. We can't run it any hotter. We start melting the silicon. We can't get to the memory fast enough to drive the chip. So what people are looking at are chips that are going to have many, many processors on one core. And that's a different kind of advance in computing that we really haven't dealt with too much before. Things like Blue Gene, things like, well, Deep Blue was a parallel computer. A lot of the systems that we use to, say, simulate engineering or simulate nuclear decay for the government, things like that. We've been doing high-performance parallel computing for a long time, but not really in a general purpose way. It's been for very special purpose applications. So even though processors are getting faster and more powerful, they're getting powerful in a different way. It's not just going to run the same application, keep running it twice as fast every year or two. It's going to have to be different kinds of applications. And right now we don't know how to make those work. While I'm definitely not an expert in all that IBM's done in, say, nanotechnology or quantum, we have some of the world-class people in that space, and we developed a lot of the field. And we're looking at all kinds of interesting applications there. Some of the technology, like quantum computing, is a lot farther off from large-scale practical use, but we're learning interesting things about it that help guide the way we do chip design today. Now, nanoscale work, we use that all the time in modern chip technology. It's a way of improving things. When you start looking at what we do with carbon nanotubes, for instance, in building circuits, we're doing fascinating work there that's going to really help keep that track of progression of increased compute power, moving. But there's so much more than just the technology growth. We have to learn how to make that accessible to large numbers of programmers. Right now, doing large-scale parallel processing like we do with, say, Blue Gene takes some very specialized training to do, and it's not something that everybody who could, say, write some JavaScript and build a web page could get at. So how do you make that technology accessible? How do you let people at the new power to create new kinds of innovation and business value? That's the thing that we worry about a lot, besides just the technology advancement. IBM's been involved in this particular field in AI as long as it's been around. Things like Deep Blue was the result of 30 years of research that IBM funded not only internally, but we also funded a lot of work in universities and collaborated with other companies. And in fact, our research model now is moving much more to an open collaborative model with universities, where and small companies as well. I mean, you obviously run into issues. Small companies there to try to make their mark, to make money, and their need to make a profit off of something may not jive with what IBM wants to do with the same technology. So there's always issues about working out how to collaborate and how to share the benefits. The same is true actually with universities who focus so much more on getting value for the intellectual property they create as part of research. But we're always interested in collaborating with people when it makes good business sense for our customers, and we find that to be very common. We do lots of work with different folks, both startups, universities, and other large companies. It's an amazing collection of people with extremely broad views. People who are philosophers trying to figure out where humanity's going. People who are engineers who are trying to make something work that hasn't been made before. Everywhere in between. People who are afraid of where technology might be taking us. People who are excited about it. A whole collection of those people and the kind of open exchange that this event has generated, I think, is very positive. I think, one, we're going to find some useful dialogue and ways of discussing these things, even for people who are very polarized on these issues, to make good progress. And I hope we continue doing these on an annual basis, as I think it's very worthwhile.